G'day team, welcome back to another video, and today we're going to revisit kinematics. Now, we did look at this in our Introductory to Differential Calculus playlist, but it's good to see another example and just a refresher of what all the definitions and what all the things actually mean. So to start with, we've got something called displacement, and now for those doing physics as well, we know displacement is how far away from the origin in a certain direction we are. We denote that function with s of t, so we're doing it with respect to time. Now, if displacement is greater than 0, we are to the right of the origin, and if displacement is less than 0, we are to the left of the origin. Now, those that know physics know what comes next, and that is velocity. Okay, so velocity is how fast we are moving in a certain direction. So v of t is the derivative of my displacement function. And if the velocity is greater than 0, we're moving right. If the velocity is less than 0, we're moving left. And then after velocity, we get acceleration. And acceleration is the derivative of the velocity or the second derivative of the displacement. If the acceleration is greater than 0, we're increasing our velocity. If our acceleration is less than 0, we're decreasing our velocity. And then if the signs of velocity and acceleration are the same, then my speed increases. If the signs are different, then the speed decreases. And we use our sign diagrams to really clearly show that. So one other thing I want to get you used to is some of the language that they may use. Okay, so I've got initial conditions when t equals 0 for displacement, velocity, and acceleration. If I want at the origin, I've got my displacement equals 0. If I want where it's not moving stationary, reverses or changes direction, or the minimum/maximum displacement, then I look at velocity equals 0 and solve for t. Then if I want constant velocity or maximum/minimum velocity, I look at my acceleration there equal to 0. So referring back to that is going to be really helpful when a question asks us for a certain thing. What is it actually asking us to solve / and what does it mean? So we're going to have a look at a nice basic question here. So I've got an object moving in a straight line with location from origin given by the displacement with respect to t, and it's t squared takes 6t plus 7 meters. Now remember, t is time, so t has to be greater than or equal to 0. So part A, we're going to find v of t and a of t and draw the sign diagrams. So let's do that now. So we know v of t is the derivative of s of t. So that's s dash of t. And that is equal to 2t take 6. Now for a sign diagram, we want to solve when that's equal to 0. So 2t take 6 equals 0. So t equals 3. Now for kinematic sign diagrams, we put 0 on the end and then our arrow. Now that's because t, like we said before, can't be negative. All right. So then I've got my 3 in here. This is my v of t sign diagram. Now if I substitute in, say, 1 here, I get a negative value. If I substitute in 4, I get a positive. So there's my sign diagram there. Now a of t, or acceleration, is just the derivative of my velocity, which is just 2. So that means there's nowhere that my acceleration is equal to 0 because there's no t in my function. So that means it is just positive 2 all of the time, so it's always positive. But we still do our sign diagram with our 0 limit. T, a of t, so 0, that's still blanked out, but over all time, I've got a positive acceleration. So they're my two sign diagrams. Now part B is the initial conditions. So that's when t is 0, but I need s of 0, I need v of 0, and I need a of 0. Now s of 0, looking back up at my function, is 7. So back up here, it's just the number left by itself. So I've got 7 meters. Because that's positive, I'm right of the origin. Now v of 0, I put 0 into here and I'm left with -6 meters per second. So that means moving leftward at that velocity, so at 6 meters per second. Then always, like I said before, my acceleration is going to be 2 meters per second squared. So that means my velocity is increasing. All right, so they're my initial conditions. Now, part C, what position where the object changes directions? Now, that is also when it reverses. So when I look back up at my table, reverses, it's when velocity is 0. Now, we've already found that. That was my t equals 3. So we know my object reverses at t equals 3. We want to find the position of that reversing, so s of 3, that displacement. Now, that displacement is when I put 3 into this equation here, and that gives me out negative 2 meters. So I'm 2 meters left of the origin. Part D, draw a motion diagram for t between 0 and 5. Now, we don't know the position at t equals 5 yet, so let's find that now. So we've got s of 5, so I've got 5 squared minus, and let's just jump back up quickly, 6 times 5 plus 7, which equals positive 2 meters. So I know initially I'm 7 meters right at the origin, moving left, and then I turn around at negative 2 meters, and then at 5 seconds I'm at positive 2 meters, so right of the origin. So that gives me a bit of an idea of the scale I need for my displacement motion graph. Now, if I have 6 here, and I work my way back, there's my origin, and then I've got my left of the origin there. So I know I start at 7, all right? That's my starting point. That is t equals 0. Then I know I turn around when I reach negative 2. So I'm going to put a little dot just a little bit above where I put the first dot at negative 2. And then I also finish, so this is at t equals 3. Then I know I finish at positive 2 at t equals 5. So again, a little bit higher at 2, and that's t equals 5. And now we just draw a nice curve between those points. So I'm going to draw a nice straight line to about there, then get my curve, and then a nice straight line to there. And that maps the displacement across time in the first 5 seconds of my object. All right, jumping back up to E, where is the object speed increasing? We know it's increasing when the sine of v of t and the sine of a and t are the same. A and t is always positive, and v of t is positive when t is greater than or equal to 3. So that is the interval. So speed increases when t is greater than or equal to 3 seconds. Okay, so that was when both signs were positive. And finally, F, the distance traveled in 5 seconds. We're looking at total displacement that has been achieved by or total distance, not displacement. Two very different things. We're looking at total distance traveled. So from t equals 0 to t equals 3, we started at 7 and ended up at negative 2. So that is 9 meters traveled. Okay, so we don't worry about negatives. We go just add up all the way till we get to here. Then but from t equals 3 to t equals 5, we traveled 4 meters. So in total, we traveled 13 meters in 5 seconds. Hopefully this gives you a bit of an idea of motion graphs and what a bit of the language in kinematics means. And thank you for watching, and we'll see you in the next video.